Get rid of this. Okay, so, yeah, I don't care about your update. Okay, so, now there are plenty of programming courses over in CS where you can really learn how to program, but if you don't know any programming at all, you ought to know a little bit to criticize programming, and it is, for some reason, it has evolved that there are two categories of computer experts required everywhere. You need a bunch of programmers who focus on making things look good and run fast, but don't know anything about security, to write crappy products, and then you hire a separate team of security people to fix all the holes in it. And this doesn't make a lot of sense, but that's the way it really is. And if you take the programming classes and get an A in them and read the textbook and the training manuals, they will teach you to write another generation of the same buggy code that has the same problems, because somehow they don't regard security as part of their job. This will probably change someday, but it's not changing anytime soon. So it's job security for both of us, and maybe it'll always stay this way because those two roles are different. But anyway, it means that since the programmers don't know security, it is necessary for the security people to learn some programming, because you have to understand what causes problems and how to fix them. You don't need to be a very good programmer, though, because being a good programmer involves handling a very complicated job, testing routines and getting all the bugs out, making your routines compatible with routines written by other people on the team, and a whole lot of other things which are not really necessary for the security tester. But so anyway, but you should know some programming, and it's certainly to get a job. When I go to the internship class, almost everybody that hires people wants you to know at least one language. So if you only know one language, you typically learn Python. Most hackers learn Python because it's very easy to write very simple programs to do something in Python. Languages like C++ and Java are much more complicated and confusing to write. And if you just want to get a simple thing done, Python is usually the fastest, easiest way to get it done. Although Bash shell scripting is pretty good too, but it's not really powerful enough. There's too many things you can't easily do with Bash shell scripts. Python is the best thing to learn if you only know one language. But the more you know, the better. Anyway, so we'll talk about the simplest problems of common programs and how to spot them and what they mean. So the fourth point of programs is you write this stuff in this artificial language, and every little mistake you make causes a problem. Now, some mistakes, like a missing comma or parentheses, are so bad that it won't even compile, and the computer will refuse to accept it, and it'll force you to fix those. It'll say error on line 7, error on line 10, until you get rid of that. But there are other mistakes, and the most damning ones are logic mistakes, where you have failed to really think this through. And I probably mentioned this before, but one fine example is the USB thumbpad reader. This was a thing you would get in the days of Windows XP. Apple had a version and Microsoft had a version. They will sell you USB thumbpad readers so you can go to biometric authentication for your computer. And the way it works is you press your thumbpad on the reader, it looks up your password in a database, and it types in your password for you. And that means the thumbpad reader software has to have your password stored in clear text on the machine, which is a huge security hole. Most operating systems gave that up in the 90s. There's not been an operating system for at least 15 years that you could buy that would store your password in plain text on the machine. But if you had this device, it has to. So it never should have been produced at all. This is a gigantic security error, and it's not a bug, it's a logic flaw. Whoever designed it had no clue about security, and apparently there was no security review from anybody that did. Yeah?
It had to be stored in clear text?
Yeah, because they didn't want to change the login system in the machine. So the login system expects to see your password, so they made the device type in your password. Now they should have, which is I think what Windows 10 has, and I think Windows 8 had it too, they switched to an alternative authentication scheme where they will take biometric stuff directly and store some kind of hash of that so it is recognized, but it doesn't involve typing in your password. This was also true of, I think Windows 8 had a thing called picture login, where you could like draw a picture with your finger, like a circle or a dot or something, and that would then compel it to type in your password. It was the same kind of mistake. Anyway, this is those are big issues. Anyway, so there's a lot of bugs in code, really quite a few. But the fundamental point, not every language is a programming language. This is the definition of a programming language, and this stuff goes back to Turing. Turing was the genius that invented modern computing, and we'll talk more about his stuff later, but he defined basically what a computer can do. And computers are little engines that can solve a certain type of problem. They can basically solve a problem if you can specify exactly what steps to go through. They cannot solve anything that isn't got so many steps, although there's now artificial intelligent learning machines that are actually coming of age where you can actually train a computer to do something the way you might train a dog or a human, and they can figure out how to do it, and you did not tell them the steps. Like they can just play a game and you tell them if they won or lost, and they'll eventually develop their own strategies the way people do. But those are not in common use yet. Anyway, so the one of the things a programming language has to have is branching, looping, and testing. And almost all of them have functions, which makes them structured languages, where you can define a small task and do just one task and tie together little functions. It just makes it more efficient to do programming. So branching is where you somehow can move from one part of the program to another part, like go to or call a subroutine. Looping is where you can do something over and over until some kind of condition is met, like for a certain number of times. And testing is where you can compare two things and decide if they're equal or not, or make some kind of statement that is true or false, and you can do one thing if it's true and another thing if it's false. And you need all three of those things, or you're not a so-called NP-complete programming language. You're not going to be able to solve all the problems that computers should be able to solve. So C, simplest C program looks like this. And let me just make a couple of these live. So by the way, Ubuntu Linux doesn't include compiling compiler by default, which is extremely rude, but Corley does. So let me open up a Corley. That looks fine. All right. And let's see, make this big. I said, make this big. Not listening to me. There, now it's listening to me. All right. So let's see where I am. Okay, let's make demo. Make dir demo. CD demo. Okay, now I got a nice empty directory. So I'll nano hello.c, and it's going to be main. And I need includes stdio. Okay, let's put that up there. All right, so this includes statements. Includes libraries that I didn't write. And there's always a bunch of boring stuff that you don't want to write. You want to use somebody else's. So I include standardIO.h, and I think I put it in those things. Yeah, all right. So that includes a library with standard IO routines, and one of them is printf. So I can do printf hello, and then I can do this, and I'll put in a carriage return just to be less irritating. All right. So this is what almost everybody does. They make a hello world. I remember, this is the seminal moment in your life. I remember in like 1974 when I got a Commodore VIC-20, and before that, it was the Sinclair with 1K, and I managed to put a single @ character on the screen in assembly language. And I was so happy. I said, yes, I can do anything now. And so I wrote, I had 1K of RAM, so I couldn't do all that much of anything, but I could do some stuff. Anyway, so now that program will not run because it's a source code. You have to compile it with GCC, so you specify the output file, hello, and the input file is hello.c. And if I made a typo, it would now complain, missing semicolon or something, but if I didn't, it'll make this executable file hello, and when you run it, it says hello. Okay, so that's all. This is what everybody starts with, your hello world program. Then we're going to mess it up and get in trouble. But the point is, any mistake, no matter how small, will cause it to crash. Most mistakes will cause it to crash. Some mistakes will cause it to do the wrong thing but not crash, and that's much more dangerous because then you actually mass produce it and sell it, and then somebody finds that there's a way to trick it into doing something unexpected, and that's why you end up in the world of hacking. So you can put in comments with these /* characters, and this is a good idea so you remember what you did. A month later, even you can't read your own code. You can't remember what you were thinking. And it's a very good idea to get in the habit of having long expressive variable names so you know what things stand for, because even though right now you remember what A is and B is and C, when you come back 2 months later, you no longer remember which one is A, which one is B, which one is C. So then there's branching and testing, and this is where you start getting in trouble. So here's a very simple program that will read your age, and if your age is greater than 0, it'll print, but if your age is not greater than 0, it won't print it. So it starts in the main routine, then it calls printf and switches control down to the printf routine, which came from the library, does a print, and when it's done, it has to go up from the printf routine back to main, and then it has to do this for scanf. And this step where it comes back is where you take over the machine. All you have to do is, while it's down in the subroutine, you trick this, you overwrite the stack, so you change the return address. This is a buffer overflow exploit, which is the #1 computers are taken over until about 5 years ago. All the defenses came up and it became less popular. Now it's maybe 5 or 10% of attacks. But there's a time when it was like 80% of all attacks were buffer overflow exploits. And because if you can trick it, if you can change this number, you can cause it, instead of returning to resume the program, to jump somewhere and run your code, and that's how you take over a computer. I can inject code in some field where I was supposed to put in something like a username or password, and I can trick it into running that code, and now I own the box. And we do this a lot in the exploit development class. It's the simplest, it's the most powerful kind of attack to understand. It was the first one that all the hackers learned, and all the others are derived from it. a hacker with the pseudonym of Aleph Null, published it in Frack magazine. If you haven't read Frack, you should probably take a look at it as sort of a rite of passage. The PHRACK. This is where all these hacking tools came from, and they're still going. This magazine is very technical, very advanced. I very rarely understand much of anything in this bloody thing, but it is where all the real hardcore binary hackers publish their new stuff. It's Frack magazine, comes out all the time. It's always just plain ASCII, and these guys are very proud of themselves, and it's a very cult-like group of super binary experts that write stuff. And in Frack magazine, Aleph Null wrote the first explanation, Smashing the Stack for Fun and Profit, which is how buffer overflow exploits worked, and that was when everybody learned how to do it. He wrote the first really clear tutorial that you could understand, teaching you how to do this. And that led to a whole generation of attack tools. So anyway, you might take a look at that thing sometime. But everything you're reading is basically something in Frack from 10 years ago made much simpler. Everything in your textbook. So looping, you do things over and over, and this is another huge problem. And most of the serious security problems in compiled code come from C. C is designed to be really fast and really efficient, but it does that by having no safety controls at all. It's if you have a car, you can have an automatic transmission and it's easy to drive, but it's not very efficient. If you get a manual transmission, you have to control the gear. But C is more like not even having a steering wheel, but just reaching into the engine with like wrenches and screwdrivers to drive your car. You have to really know what you're doing. It places a lot of burden on the programmer. And here's one of the many problems. Typically a loop goes like this. For I equals 0, I less than 11, I plus plus, print this thing. So how many times is that going to print? What do you think? 10. No, not 10.
That's a 5.
It's going to print for 0, then it's going to add 1 and print for 1. It's going to keep going as long as I is less than 11, so it's going to go 0 through 10. It's going to print 11 times. That's an off by 1 error. This happens all the time. And if you start it at 1, it'll be different. If you make this less than or equal, it'll be different. So what happens is every time you write a loop in C, you have a high chance of being wrong about how many times it's going to go through. Now here's a long extinct language called BASIC, which is where I started in 1974. And in that language, you just write for I equals 1 to 10. Do something next I. The whole point of this language was to be easy. You never got the wrong number this way. It was dirt simple. You knew this was going to happen 10 times, it happened 10 times. Nobody ever really knows how many times it's going to happen in C. Even the most experienced programmer frequently makes a mistake, so something happens at extra time or not as many times. It's very common. It's one of the big common errors. It's a language that is unforgiving. It does exactly what you say no matter how stupid it is. It never questions you. It never corrects what looks like a mistake. It just does what you tell it to do, so you have to be perfect. And no programmer is perfect, so this is one of the common errors. So you loop. An algorithm is the term for the steps of your program. A flowchart, these are the things to do in some order. Bugs or errors in your code that cause a problem. And pseudocode is what most people do. Beginning coders in like programming classes will read their homework problem and immediately start typing on the computer, and this is a punk amateur move. This is self-defeating. Professional programmers spend 80% of their time planning before they write a single line of code. They write a block diagram, they write pseudocode, they plan, what do I need? I need a routine here, this one's going to call that one, this data is going to go this way, that data is going to go that way, and they think it through, because your first idea is almost always wrong. You'll write this stuff, and then you'll say, wait a minute, this is never going to work, I need to do it all different. So professionals spend most of their time planning, and then they write what they plan to write. So you start with pseudocode, where you just write things like this. Like if you go to shop, you have the function that purchases ingredients. The purchase ingredients has get car, drive to store, then purchase stuff. And then you have another thing like cut up ingredients, another thing like do the dishes, various things, subroutines that do little pieces of the job. And then your main program just calls all these subroutines. Do this bit, do this bit, do this bit. You document this stuff with comments or other documents. Most people that like to write programs hate to write comments and documents, and most companies force them to. So they fire you if you don't document your stuff properly, because they learn that if you hire a bunch of programmers and then some of them quit and you hire new guys, they can't figure out what's going on. It's usually more efficient to just write it all over again than to try to figure out poorly documented code. And as you want to upgrade and add new features and fix the bugs, it's more and more annoying not to have good documentation. So there's an industry standard, which is like 2 to 3% bugs, which is really high. And I don't know where they got this number. I know Linux has much less, 0.17 bugs per 1,000 lines of code. And this people can know because Linux is open source. So you can totally get all the code and you can totally audit it and run it through test programs. And Linux code is very high quality. The Linux people really value precision and logic and efficiency. And they'll really give, like you do something stupid in Linux, Linus will just swear at you and abuse you and kick you out of things. They really value logic and perfection much more than anybody else. Yeah?
So is it just a bunch of like people that are experienced in coding, they just like upload their code to a repository or something?
Yes, yeah.
So anybody can do it?
Anybody can do it. And by the way, if you contribute to an open source project, this is a really good way to advance your career. Even if you can't get a job, this counts as experience, and you can have non-technical contributions. By the way, every open source project is in desperate need of PR and help desk kind of documentation because I've been to so many things, so many tweets. I have this new thing, I go there, it has a name that means nothing, I see nothing but a page of code. I say, what does it do? Why do I care? There's not a word. This is more common than not. They'll babble about something technical that I can't even understand, and they don't tell me, what does it do? Yeah.
Many companies, big companies, they also allow their employees to contribute to this particular amount of time for Linux.
Oh, yes.
They just like during this work time.
Yes, and they say like 80% of coders, in fact, people are getting paid by a company. They're not just volunteers. But this is what I'm saying. If I had a company and you make some kind of product and you could write your own operating system, it would be much more efficient to just use Linux and join this community and let your code and then make minor modifications to Linux. That would save you a lot of time, and then you can donate that code to the world. This is what Google does. They donate code to the open source, and then you're just part of a giant community of people working together, and you don't have to invent everything yourself. Anyway, so Windows 2000 had, 1 per 1,000 lines, much less than that standard, because the source code leaked for Windows 2000. They were able to go through it. It's proprietary. Microsoft doesn't release their source code very often, but occasionally they're forced to for various reasons. But anyway, that's still an awful lot of bugs. 60,000 bugs in Windows 2000 because it's 50 million lines of code. That's why you will never get rid of the bugs. You will never get rid of all the security vulnerabilities in anything. It's all too big, and every time they bring out a patch, they just get a small fraction of the bugs and introduce new bugs. Nothing is ever perfect. Of course, why did anybody ever imagine anything was perfect? People aren't perfect. Material objects aren't perfect. Your food and water supply isn't perfect. Everything you deal with is imperfect, including all your computer code. So C was developed at Bell Labs. It was designed so you could unify computing. Because you had C, you could write Unix in various platforms, and you could finally, it used to be before this, that if you bought a mainframe computer like an Amdahl that we had, it would come with a stack of manuals of how to run this computer. And if you had an IBM, it had a totally different language and totally different hardware, and there was nothing similar about them. And so you couldn't have the internet because they couldn't even talk to each other. So in order to make the internet possible, they invented Unix to be the unifying language that would run on every computer, and they invented C to be the language that you write Unix in. And then every hardware manufacturer, instead of writing they just had to write a C compiler for their hardware, and then you could compile Unix, and then they could talk to each other on the internet because they're all speaking the same language. Yeah?
I just want to ask a question. Where is C mostly used?
It's used in Linux mostly. And now, and a whole lot of it is still C, some of it is C++, which is the enhancement. Most of it is still C, most of the heart of it.
Wait, would you say that again?
C was the original language, and C++ is an enhancement to make it object-oriented. And most of the code in Linux is still C. But for some projects, you go to C++ to get the more advanced features. Yeah? I thought you had a question. Anyway, so that's the game. Now everything that actually runs in your machine is really binary machine code. It's just hexadecimal bits like Wireshark capture, but you can make it slightly more readable by running it through a disassembly. So you'll see commands like push 70 on the stack, push some kind of offset on the stack, call a subroutine at this location, so it will stop executing this code and jump down to some other code and run it, and then come back to this code. And these commands that's assembly language. You learn to write that stuff, which is very hard to write in. Every command does very little. It just moves like a few bytes around, and it takes hundreds of thousands of commands to accomplish anything. But that's what you have to learn if you really want to get into the binary attack. But what most people prefer to write in is a higher language, easier to read, like C. And that is then compiled down to assembly language and run there. So, like I say, if you use Ubuntu, you have to install the C compiler with Build Essential, but it's included in Corley. So you got comments, you got the include statement, which is how you put in libraries that somebody else wrote, and there's dozens of libraries that come along with C to do most things you want to use. And you can make functions. So you start, the main function is every C program has to have a main function, which is where it starts. You have these parentheses here in which you can put arguments if there are any, and you have these curly braces that define the beginning and the end of it. And every line has to end with a semicolon. That's because white space means nothing in C. Tabs and spaces and line feeds mean nothing. The most difficult thing for me about Python was white space means something in Python. And I was used to C, and I was very frustrated at all the weird errors you get in Python. Because in C, you can just space it out any way you want. That doesn't matter. That's why you have the semicolon and the curly braces. That's what matters. Yeah?
So are there any examples of why a security tester would write something in assembly versus just writing it in an object?
Oh, yeah, yeah. You have to take the exploit development class. We talk about this. One common thing is you want to write shellcode. And so you find like an overflow vulnerability but you can only put in like 50 characters. That's all you have room for. So now you have to write code that will accomplish something that's only 50 bytes long. And that you have to go to assembly to do that. And that's why anybody writes assembly. The main reason you write assembly is because you really need efficiency. I used to do human vision experiments years ago, testing the ability of humans to see things, and I wrote all this stuff in assembler because it had to be precise, down to like the microsecond. So if you write in a high level language, it gets translated through system processes and it's sort of vague. But if you write in assembler, you can control exactly when things happen and make them as fast as possible. But it's much more expensive. So what you do is you focus on just the critical part of the code, and somebody would write that in assembler, and the rest of it you write in a higher level language. And the reason why C is so popular is C is almost as fast as assembler, and it's much easier to write. Other languages like Visual Basic are much easier to write, but they're very far from assembler, so it's much less efficient as they compile. The code will be bigger and slower. So functions can call other functions, so you can make a main function, and it can then call a function here. It calls the printf function, and after it prints it, then returns back to the main function. And you can declare variables, and you have to in C. It's a structured language, so this is part of where we're going to get in trouble. You have to tell it. There's a few variable types, integer and float and string, and you have to tell it this is an integer variable, so it can only hold numbers, and only numbers up to a certain size. After that, it will roll over like an odometer. So if you just keep adding 1 to it, it'll add up to about 2 million, and then it'll roll back to negative, which can get you. Yeah?
So how far is C++ from the...
C++ is the same as C, and then it adds extra features which makes things object-oriented, which we'll talk about a bit later, but object-oriented makes a container, a data structure called an object, which you can then make other objects from. So it's just a way to make it more versatile at a higher level. But inside, it still looks like C.
Okay.
All right, so there's integer and float and double precision variables and characters and strings and other kinds of variable types in C. So when you use a variable in C, you specify how big it is. But you can specify a variable and then abuse it, and C will not protect you. Yeah?
Is there a variable of the string, or this is just an array of characters?
There are string variables too. That would be a pointer to an array. Yeah. So you can math on things like the I++ here, that adds 1. It starts at 0, and every time it executes this, it adds 1 to it. That's a shortcut for I equals I+1. And so you got addition and subtraction and division and modulus and all the mathematical operations you want are available, of course. And you have logical operators like I less than 11. If I is less than 11, that is true. If I is not less than 11, that is false. That's a Boolean or logical argument, and you need that for branching. You have to have something that's either true or false, and then you go one way or the other. And use double equals for equals, less than and greater than, less than or equals, and so on. You have various kinds of comparisons you can do to make those logical constructs. So let's screw up C. So let's improve my hello. Let's copy the old hello to hello 2. All right, and here's my next version of hello. All right, so now I want to echo back your name. So I'm going to make a character, name sub 10. That reserves enough space for 10 letters. Then I'm going to print f, what is your name? All right, and then scanf into, I'm going to call it a string, tell it string data, and put that in name. All right, and now I can say hello, %s, and put the name here. So it's going to ask me my name, and then it's going to print back my name, unless I followed it up, which is entirely possible. So let's try compiling that one, which is GCC, output hello2, hello2.c. All right. Well, I guess there's no major typo in it. It didn't complain about compiling. Let's run hello2. Okay, my name is Sam. It says hello Sam. Okay, so it works. That's fine. But suppose my name is this. Now I get segmentation fault. Now this is because I've reserved space for 10 characters, and a sensible language like Visual Basic, if I have space for 10 characters and then I put in 30, it will just go reserve 30 characters space somewhere else to make room. But C will never question your orders, no matter how stupid they are. Take a 1 gallon bucket, yes sir. Put 100 gallons of stuff in it, yes sir, no problem at all. I'll just do it, it spills all over the place, but you must have planned for that because I would never question my orders. Download this virus, run it, reformat the hard drive, tell them anything you say, it just does, never questions. So that's the problem with C. You're supposed to be smart enough to anticipate all these problems and plan for them, and nobody is, so we have all these vulnerabilities to exploit. So anyway, that's the problem. Yeah.
There was an exercise, homework exercise,
Yeah.
which was doing this.
Yes, you write a few of these. That's right. And you get to see it. And if you take the exploit development class, we go further where we develop the attack and take over the machine through it. Here we just observe that it crashes.
In the homework exercise, if you give the array was 10,
Yeah.
but if you give 20, it wasn't set fault.
Yes.
If you give 30, it was fault.
That's right. It won't crash just because you go a little bit over. And that we're going to get there. That's because you exceed the space for this variable. So you start overriding other parts of memory you're not supposed to go in. And that causes minor problems, but it doesn't cause it to crash until you go outside your stack frame. We'll get back to that. But you're right, overflowing a buffer a little bit does not have an immediate disastrous effect. You have to overflow it by quite a bit before it completely crashes the program. And in fact, good, right up to this picture. So here's the point. When you call a subroutine, like printf, you have what's called a stack frame. The stack is here, and so you have the program running up here, the main program is running, and then you have, when you call a subroutine, it pushes a bunch more things on the stack. It defines this group of this space of memory called a stack frame. And that includes the local variables for this routine. And so it'll have the name and whatever other variables here, like I and whatever else. And then at the end of the stack frame, it will store the return pointer right here, the extended, which is where to go when I'm done. So you'll do whatever you're doing in this routine, and when you hit the end of the routine or return statement, it will take this value and jump up to that code. And this would normally point back up here to the main function. So if you have a buffer overflow where I can feed in data and exceed the memory reserved for my data, I have 20 characters for name, but I can put in 100 characters. I can overwrite that. Then after I go to 21, 22, 25, I'm writing on other variables. But those other variables might not really matter very much. But if I go all the way down here and change this return pointer, then when it tries to return, it will jump to some random value. And that will cause the machine to crash, and that's what you saw there, stack smashing. So the goal, the way to take over a machine is you carefully make an exploit that puts a special value here, and then you keep going, and down here you put no operation commands and egg. The egg is your attack code, which you have, which is machine language code that will take over the machine, do whatever you want. Typically what you want is for it to open a listening network socket and give you a command prompt so you can remotely control the machine. But you can do other things like crash the machine, make a new administrator account, or anything you want. You write this code that does whatever you're trying to do, you put a whole bunch of no operations in front of it, and then you have to determine this value. If you can predict this value, and you do not have to get it exact, if you can jump down to any of these numbers, it will, no operation does nothing. It is nothing, 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 and then runs your egg. So if I jump right to the egg, that would be fine. But if I jump 100 bytes before the egg, that would be fine too, because it'll just do nop, 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 and run my egg. They call this a nop sled. You slide down the sled, and you take over the machine. I just have to be able to get close to guessing where that code I put in is. So for this to work, I have to be able to carefully target the instruction pointer by putting in enough bytes of junk to hit it, and then I have to be able to figure out where my injected code is so I can jump to it and run it. And those things were not too hard to do in earlier versions of operating systems, and because everybody and their brother took over everything with buffer overflow exploits, a bunch of defenses were built into operating systems, and we'll talk about them as we go ahead here. So to prevent this, one of the simplest defenses and extremely powerful is address space layout randomization, which came out with Windows Vista. And what you do here, before this, Windows machines would just use memory in order. So you boot up Windows, Windows would just use low memory. Then your antivirus comes on, it just uses more memory. Your web server comes up, your SQL server comes up. Every program would just go next in memory, the simplest way to use RAM. And that means I could predict where I was. I could just take a copy of Windows, install the same kind of machine. I could pretty much guess where your web server is. So when I inject code in the web server, I could pretty much guess where it's going to live. So to prevent that, they put in address space layout randomization, which means every time you reboot the machine, it just randomly assigns memory locations to all these things. And that means it's very hard to tell where you are. So even if I can inject code, I can't find it to run it. And this turned out to be a very powerful defense. Unfortunately, as you will find is always the case, when Microsoft makes an improvement like this and they brag about how great it is, it's almost always lame and they only did half of what they said they did. So in Microsoft operating systems, they didn't actually randomize all the Windows functions. A bunch of them don't move because it was too difficult to write the code. And when they do code, they didn't really make it random. A lot of it only has like 8 or 12 bits of entropy. So they really only grew to like 1 of 256 possible places. So all you have to do is run your exploit 300 times until you get lucky. But it is an improvement. This is a much more powerful one. This is a motherboard feature called the NX bit, and it's been around for a long time, and modern operating systems implement it. So what you do is you mark this entire area non-executable, because this is supposed to be used to store variables in routines, the stack. The stack is non-executable. So now, if the programmer makes the same programming mistake, the name is 20, but I can put in more than 20. I can overwrite this. I can put a value here. I can put in the NOP sled. I can put in my egg. But when I jump, it won't run because this code is non-executable. So it will not let me take over the machine, even if I can inject something. This is pretty cool. And the way to overcome it is return-oriented programming, where you take code that is already in the operating system and you patch it, a couple of assembly instructions at a time, like cutting letters out of a newspaper to spell out a message, and you build code that does your attack. Or, more precisely, we use Mona, which is an IDA Pro plugin, and Mona will build code that turns off NX. It's a feature that can be turned on and off, and you can find enough assembly language to piece together stuff that will turn it off without injecting code. But that took a long time to work out. It set the hackers back a couple of years. You know, these are good defenses. These raised the bar quite a bit. All the old attacks don't work anymore, and it took years to make new attacks that work. That's all you can ever have. The cops get bigger guns, the cooks get bigger guns, nothing's ever perfect. All you can ever do is hold back the current crop of attacks, and in a couple of years, they'll be coming over the wall again, and you'll have to build the wall higher. That's the way it always is. Another one was canary values. What you can do is every time you jump into a subroutine, it writes a random number at the end of the stacked frame, and when it goes to return, it makes sure that that number has not changed. And that means nobody has done this. And if anybody has done that, it stops. It says stack smashing detected. I'm not going to run this program anymore because it has been corrupted by somebody. And so the attacker, again, does not get to take over the machine. They can inject this stuff and they can put in the return value, but it won't run the return value because it detects that the stack has been smashed. And that's difficult, although there are ways around it. One way around it is sometimes that random value is not random enough and you can find a way to predict it or a way to read it. And sometimes you can find a way to read it and rewrite the right value on there. But and you can also sometimes, there's another kind of stack overflow, which you're doing in the exploit development class and in the web class, you're doing this one, where I do an overflow that doesn't get this. It just leaks from one variable into another variable, so I change that variable. And then if that variable is used in a useful way, I can still take over the machine. But that's less common because it would require a combination of rare circumstances. But, you know, it weakens the exploits, and that's what defenses are supposed to do. The old attacks don't work, and the new attacks have to look for more subtle problems. Anyway, so I got a few icebreaker questions about that stuff. Come grab one if you need one. There we go. See how I make this big. There we go. All right. So, what's the essential part of every programming language? Whoa, that's the wrong thing. That's what I was trying to do. There we go. All right.
Good point.
guess I'll quit at 35. All right, and you need to have all three of them. Now, of course, you have pretty much everyone got. That's good. You got to have those three things. There are plenty of languages out there, like HTML, that are not programming languages. They do something, but they don't have branching, looping, and testing, so they are not programming languages, and they cannot solve this class of mathematical problems called NP complete. Yeah.
How is looping different from branching?
I think technically the branch is just one if-then, and the loop is the construct that does something many times. I know you implement it with just an if. It's a good question. I don't know. It's technically a different logical thing. There must be some way to define a branch that does not make a loop possible, but one doesn't occur to me right away. Perhaps if you couldn't increment variables. If you could not increment variables, because it doesn't say you have to have variables. You have to have branching, looping. So I think in an abstract philosophical sense, they're different. If you have numeric variables, it's obvious they both come together. But without those, you can. I know this all started with the Turing machine, which doesn't really have variables. It's a very different thing. Anyway, so over in CS, I bet they teach you that. That's what they know that I don't know. Anyway, so all right. What's the binary language built into the processor? I'll quit at 30. All right, so that's machine language. It's built into the processor, and this is actually the heart of a really worrisome problem. There are bugs in the processor itself. There are 100 known bugs in the Pentium 4, and I don't know how many there are in later versions, and you can't fix them because you have to buy a new processor. There's no way to change it. There's no way to patch it. So they try to work around it with firmware patches on the motherboard. But what's even worse is, this is a huge problem. Suppose somebody puts Trojans in the hardware. Suppose your processor has some extra command that's not documented that does something evil, like put it under remote control or self-destruct. It could be there, and there's no way to audit it. There's no way to know, and they are very concerned about this. This is why the U.S. military several years ago said they want to stop using Chinese chips, because we don't get along with China, and they could totally be poisoning the chips. And we're still using Chinese chips because we're not willing to pollute our water supply, which is what it costs by making them here, and they are. So it's actually hardware Trojans. People are very scared of these. What if your hardware was poisoned? Your antivirus will never find it. Your firewall will never find it. It's actually very hard to know and very hard to stop. Yeah.
I don't understand why there's no way to audit for it or find it if it's possible to change it.
It's not possible to change it. You couldn't. All you can do is take out the chip and throw it away.
Right, but what I'm saying is to infect it in the first place.
Oh, you'd have to do it when you designed it.
Yeah.
So the people that manufacture your chip could give it extra commands that they don't tell you about, and you would never know. So there could be extra commands like, and there's suspicion. There was Israel sold military hardware to the neighbors, and then they had a war with Jordan, and they were using Israeli radar, and the radar mysteriously failed to detect the bombs coming from Israel, and they suspected that it was sabotaged. And then we're in the same case. If we go to war with China, which is not impossible, we're using Chinese chips and everything. And so this is not good. And the U.S. government's been like yelling about it, but we're not willing to have giant chip factories in America anymore because they totally pollute the water. You have to use all this horrible stuff like acetone to wash the chips and make a Superfund site out of everything. It's only China's willing to destroy their environment right now like that. Like we used to be willing in the 70s and 80s, and we're no longer willing to do that. They're getting tired of it too over there too, but then it'll be somebody like Pakistan doing it for a while. There's people that are so desperate they're willing to put up with the environmental consequences of making these chips. Anyway, that's how it goes. But if someone poisoned your hardware, boy, it's hard to sleep at night. You get thinking about that. Anyway, so.
How do they even know there's an extra command other than what's published?
You would never know. The people that make the chip would know, but the person who buys it and uses it would not know. You could perhaps write some kind of program that hunts for it, like a fuzzer, but if you didn't happen to find the magic key to turn it on, you'd never know. The other thing you could do, of course, is put it under an electron microscope and take it apart with acid and read every little thing. In principle, you could do that, but it would cost like $1 million. So the whole point of getting cheap chips would be defeated. So right now, we're all just using Chinese stuff. Yeah?
How is it not the legal responsibility of the company that's selling them here to test them?
Because nobody wants to pay what it would cost to do that kind of test, so we settle for reasonable tests. That's the point. I mean, just like all your products, I mean, if you make them test it too much, we'd all go broke because the price of food would be too high. So, yeah.
Plus, even if you do test them, there's still not the factor that those tests might not even prove anything.
Absolutely. And if you, for example, port knocking, it's very easy to make the thing that's waiting for a magic network packet to wake it up. And you could make that magic network packet 128 bytes long of random stuff. You'll never find it.
And there's always errors too, so there's that
That's right.
percentage of error that will be there that they can just say, oh, that was an error.
That's right. So, I mean, it's a problem. You're trusting all this stuff, and you really wouldn't know if it was poisoned. This is true of proprietary software like Windows. There's a persistent myth I've heard for 20 years. There's a secret backdoor password in Windows where you can get in. A lot of people believe this. There's a lot of people like me that don't believe it, but none of us can prove if it's true or not. And it's rumors always going around that Microsoft has a secret way in. They could, of course. You'll never be able to prove that's not true. Anyway,
Now they just collect your information in the open.
yeah. But anyway, so which one of these puts comments in your code?
I click from froze. I can press the button, I can turn it off.
Neat.
At
So
all.
you broke it. But anyway, I'll give you 1 point for that. Grab another one if you like, because you can't win. But I think you broke it. That's what's going on. All right, so let me take it. Maybe it needs new battery. Maybe it's just toast. All right, I'll make a note.
Check on the battery.
Yeah, the battery's still
I
on.
did not.
Actually, it seems to work for me. You just have to drop it. Yeah, drop it another time.
Now it works.
Yeah, I think it does. Just drop it if it happens again. Anyway. All right, and so this, of course, D. I think I already graded it. I did. All right, good. So let's go on and do another one of these. All right, so, all right. Which one of these do you have to have in every C program? All right, I'll quit at 25. Looks like the answers are in. All right, and you have to have main. It has to know where to start. You don't really have to have include. You could, in principle, not use any libraries, although that would be pretty difficult, but you must have main, or it doesn't even know how to start. All right. Which one of these puts library code in? And we'll see. Quit at 20. I think would be enough time. 25, I guess. And this is sort of a test of alertness. And, okay, only 4 people were asleep. Anyway, because I gave away the answer in the previous question. But anyway, so, all right, I've noticed often I give away the answer and it has no effect at all on the results. But anyway, so it just depends on how many people are asleep. The technical term for this is the teachable moment. The moment when they happen to be listening. Anyway, so let's take a 10-minute break. We'll pick up at 7:15. I'm going to stop the recording and start another one later. All right. This is chapter 7. So
Where's the
1,
sign-in
2,
sheet for
3.
the test?
Up there.
Sorry, I was late for